same damage, in theory, as if I had a nuclear bomb several kilometers away from that. I can do exactly the same damage, right? So it's all about mass and distance. So he said, well, if I say, 20 kilos of TNT 20 feet away, nobody's going to understand it. I said, you're right. Somebody might ask you, how much TNT can I fit into a car? He said, great idea. So he went on Google, how much TNT can I fit into a car? And he stopped halfway through and goes, Professor, I'm not doing this. I'm not doing this. I'm sure FBI is looking out. Okay, so let's look at how a blast actually looked like. You have this initial spike in energy, but then what happens after that? So imagine if this is the front. This is the front that actually hits the item. Could be a column, could be a wall. And then you have what we call a positive phase. So this exponential function typically represented as a triangle. So if you've seen blast presented as a triangle, it's for two reasons. One, because this decaying function is being approximated as a linear function. And the second reason is because people ignore what we call the negative phase. So the negative phase is this suction that you see. I had a video earlier to show it to you, but I might be able to show it at the end. It just didn't work on its own, so I took it out. So essentially, you see this blast hit the building, and then suddenly it retracts in a negative phase, right? Now, you see, the magnitude of the negative phase is much, much smaller than the positive phase, so you're thinking, logically, I can ignore this, right? Well, not really. Imagine if you have a window that's attached from the outside with some screws. It's bearing on the column, or whatever wall or something, structural elements you have. When the blast comes, it doesn't do damage to the window, but when you have the negative phase, you can easily withdraw those nails or screws, right? So you have to design it for both. If you have a column, and the column has the exact same dimension, and it gets hit by a positive phase, and then a negative phase, you say, okay, I will only design it for the positive phase, and I should be okay. But this is the actual shape of the blast load. So what kind of damage can we experience? The one on the left is from Oklahoma City. Obviously, there's many, many other examples. What I wanted to show you is kind of two typical examples of what you might see of a localized failure. So in this case, a very famous case study from Ronan Heights. And for that, we had a column that was taken out. So one apartment had a gas leak, there was an explosion, one column from the window went out, and the whole thing just collapsed, pancaked all the way down. Okay? So the whole building's still there. The person who lives here could, hear a noise, but really didn't care because it was not his balcony. The difference is, in this case, we have a very large truck in front, and that large truck would basically explode and send this wave front, and it will interact with different, and as you can see, this is not damaged, the back is not very damaged, so probably the actual event occurred somewhere right here. The bottom would be more affected. As you go higher up, it's going to be less and less affected because of this expansion of the pressure. So these are two typical cases of what you can see. Now, the first thing that comes to your mind is, if I'm possibly going to be exposed to blast, why would I build my building out of timber? It doesn't make sense, right? Timber is a weak material. Timber doesn't really presents itself as a blast-resisting material. Well, there are certain things in timber that are really bad from a blast perspective, and that is it's lightweight, and it's a brittle material. Right? So these two things really work against it. The positive things is every time it comes to impact, wood can absorb quite a bit of that energy because it can deform within itself. So it has some positive properties when it comes to blast. But the second reason is really that there's two cases where timber can be exposed to blast load. The first one is, you can imagine you have an embassy, somebody puts a charge in front of that embassy, it explodes, well, there's all houses around it, and I'm not exactly sure in your area how houses are. In North America, they're all made. Okay, it's all lightweight timber. The second one is, and I wish I had more pictures of this, but I don't want to waste too much of your time. The one, and I encourage you to look it up, the Richmond Oval, which was the oval arena in British Columbia during the 2010 Winter Olympic. These are glulam arches that extend about 100 meters with no intermediate support. And this is just the outside of it, the wave as it comes up. That building was actually designed for blasting. Okay? So you can imagine that iconic buildings like this would need to be designed for blast. And the other example I gave you is that you have surrounding buildings, could be any kind of building, that would be affected by some sort of a blast load. The point is, when this was done, this was before that we actually started our work on the standard provisions for blast in Canada and North America in general. So nobody really knew how to design for that building. And so we've come much, much further now, and again, I'll show you at the end a few tricks or a few equations as to what you can do. What happens if I have a blast near an iconic building, and I have small houses around it, using what we call 2x4, so essentially, 50 millimeters by 150 millimeters, or somewhere in that range of studs to build that house. This is the kind of devastation you might experience from that type of event. So what are we trying to do from a design, from an engineering point of view, is we're trying to save life. And so in order to save life, you look at the amount of pressure that could, for example, puncture your ear, puncture your internal organ. I know this is a lovely topic in the morning. Or you look at debris. So essentially, if a brick from the outside of the wall comes and hits you on the head, you could actually be significantly injured. So you look at these two things, and the code essentially tries to prevent human casualty. That's essentially what we care about. You don't really say, oh, after a blast event, I'd like my house to be still standing, still functioning. They try really to prevent casualties. About 5 years ago, when I got into this area, you of course start with looking at the state of knowledge at the time. You do your literature review, and you say, what do we know about wood under what I would call high strain rate? I'll come back to this point. Just because it relates to dynamics, and I'll come back to it, and it affects the material behavior. So it's high strain rate. Anybody knows what that means? So the difference between me taking this and loading the table as such, and I wait for maybe, or I keep loading and I wait for maybe 10 minutes or so, and then the table breaks, versus I hit the table really, really fast and I break it. The way that the table is going to respond to me is going to be a little bit different. For different material, it's going to be different. And my main interest in the beginning of the research was, how does wood behave under high strain rates? Okay, under a very, very impulsive loading that you expose it to. And so what we realize is two things. There has been some live charge, so you put a charge outside, you release it, and then you get damage. And you look at the damage, you say, holy crap, it broke. There's not really data that you can retrieve out of it, right? So that's, I'm oversimplifying. There's more there's more scientific outcome from this, but essentially that's what we found. And the second one was based on fairly old research on impact. So you take a piece of wood, in fact, you take a small piece of wood like this, and you hit it, let's say, with a bullet, or you hit it with a machine, an MTS machine that can run really, really fast. And you look at what is the impact. Impact is not exactly the same as blast. It's not in the same range of strain rate, for example. So one has to be careful of translating information. But what we saw is this from the literature, that you take whatever piece that you have, that you hit it with very, very fast. It could be if you have a beam, let's say, you could take a very large mass and you could drop it. And because it has a large mass, the impact is going to be very fast. or you take a small mass and you go with higher speed. So it's either the acceleration that you increase or the mass that you increase. Bottom line is, you see how it broke like this. Have you guys done any timber stuff here? At the material level or any other? Some of you have. So if you take a beam and you load it in timber, do you know how roughly it breaks most of the time? So you initiate a failure somewhere where, let's say we have a knot here, some sort of a defect. So you initiate a failure here. And then because wood is weaker along the shear line in this direction, it propagates this way, and then it hits maybe another knot that's stiff and it cannot continue. So it comes back again and it goes like this, and maybe it fails, right? So this is a typical failure, and it follows basically what we've known for very long, which is the path of least resistance. Why? Because timber is essentially pipes that are going in this direction, and to cut through the pipes requires much more energy than it does to go through a few of those pipes and then run along them, where the bonds are very, very weak, and then go back and forth, right? So this is the path of least resistance. As you can see here, it doesn't really follow the path of least resistance. It's almost like a karate chop. And in fact, you could do this yourself. Take a piece of wood that you can break, and try to break it. It breaks first at a certain point of the fiber, and as you're breaking it, it kind of undulates back and forth until it breaks completely. Take the same piece of wood, now you've broken it, take another piece of wood, and just karate chop it like this really, really fast. Okay? You'll see that it doesn't go and travel, take the scenic route until it fails. It fails much more across the dimension. So this is what has been observed so far. So very little has been done on this. So when I started, see, I had to buy the coffee because it scared me. So when I started there, the first thing I did was we purchased this facility which simulates the effect of blast. I mean, there's no way, it would cost me somewhere around maybe, I don't know, 150,000 Norwegian krone to have a day on the facility. Then I have to bring the charge, and then I have to build a foundation for my specimen. And it's very, very costly. This was a very cheap solution, and I'll explain it very briefly. So we have what we call the driver section, and then we have an expansion section. So the driver section builds up the pressure. We have 2 aluminum foil right here. So one aluminum foil would go here, one aluminum foil would go here. We would plug some air pressure into it on both sides. Because we have equalized pressure, the aluminum doesn't puncture. Once we take out one of the pressure, which is inside the chamber, now the total pressure is 0 on one side, maximum pressure on the other side. It punctures the aluminum, and it goes through this driver section, and then it expands. Why do I need it to expand? Because I need to even out the stresses. And this here, which essentially looks like, so this is the driver section, and this is the expansion section. This is a slice in that hemispheric pressure that I showed you earlier. And so you put something at the end of that, and you let it interact with it. One example of that would be to put a wall, or to put a column, or to put something on. We need to know what is our reference point. Well, our reference point is static testing. So you take a piece of stud or beam, and you put it into just simply static testing. You let it fail within 5, 10 minutes, 7 minutes, somewhere in that range. So that's an average rate for static testing. And you can see, this is what I was talking about before. So this is a typical failure that you get, right? And then you put it into the shot tube, and you test it as an individual stud, and you see how the failure changes quite significantly. This is one example, and this is another example where you see it's almost like cut through, cut through, cut through, right? And so this mimics what we see in impact testing quite well. So what can we do with this? This is just an example of what we love to do in the lab, just break the heck out of things. Can I just dim this?
Here's towel.
There you go. Yeah, it's good. Okay, so you just release the pressure and it just disintegrates that system. What's good about this is I can have LVDTs on one side measuring displacement. I can have strain gauges glued on the stud to know what is the strain. I have two basometric load cells inside, and when the pressure passes through them, I know the exact pressure just before it hits the specimen. So I know a lot of information about this, much more than a live test would give me. So this is the kind of damage that you see. When we did this first, you would test on smaller level of pressure, and then you would get damage to all studs. The sheathing, the OSB plywood sheathing, was capable of transferring the load to the stud. If we were to just blow it out, you see the studs some of them are still standing, and the sheathing failed from between. So that gave us an indication that the sheathing might have been a little bit too thin. Typical sheathing might have been a little bit too thin. So what we did was, and this is kind of a, not trial and error, this is really trial and learn, So you increase the sheathing thickness, and you see completely different failure, right? The sheathing now doesn't break. It bends, it breaks in the middle, but it doesn't disintegrate and becomes debris. So remember, my main focus was on limiting the amount of debris. So I gained this, but I lost something else. Now the studs are flying away, right? So the sheathing is still intact, but now the studs are flying away. The reason is, now the sheathing pushes the stud out. The stud is only attached with a nail, and that nail is in withdrawal, and that's, of course, a very weak connection. So now the studs are just flying. So instead of being hit on the head with the sheathing material, now you're hit on the head with the stud. So, go back to the drawing board. We said, okay, if it's a withdrawal issue, why don't we use screws instead of nails? So you use screws, and now we're talking, right? Now we maintain the sheathing, and we maintain most of the studs. And we looked at the studs that actually failed. Look at this one here. Half of it is here, half of it is here. We said, what the heck is going on? Well, the screws we used, the tip stopped right there. So it's right at the tip of that screw that it disintegrated. Logical would be that I would go back to the student and say, use longer screws. The student said, heck with you, I'm leaving. Right? He was done. It's like, my master's finished, I'm gone. So we didn't do it. But essentially what we showed is that if you are able to grab on the stud, and if you're able to have a thick enough sheathing, you can actually maintain the wall there without it just flying away and hitting people on the head. So this is another one that was really interesting. We said, instead of transferring the load from the sheathing to the stud and breaking the stud, which would give us ultimately the highest capacity we can have in the wall. What's the highest capacity? It's by breaking all of the studs. We said, what if we do something else? Still prevent debris from happening. What if we sacrifice the sheathing? Let the sheathing break, let the studs still stand, but what we'll do is we'll catch whatever debris comes out of the sheathing. So I don't know if you've ever worked with concrete slabs. You have something called welded wire mesh. Instead of having rebars, individual rebars, these are just a grid of rebars. We took one of those, very cheap, and we just put it at the end, and we said, okay, we'll capture those sheathing materials. So let me just show it to you again. So you'll see we're sacrificing the sheathing. What comes in is just small pieces of sheathing that will, might cut you a small scar in the face, but it's certainly not going to kill you. And so I'll show you a picture of the final damage because videos are a little bit dark. We have money, but we don't have that much money. We have money for the damn camera and equipment, but we don't have money for light. So this is what you see. So this is before the test. The welded wire mesh are simply just attached on the outside. And this is what happens. We capture all these large pieces, and you see the stud. They're all standing. What does that mean? It means I have not 100% of, I would have asked you that if you took timber design course, but I'm not going to do that mean. We don't have 100% of the axial capacity of the stud, but we have the stud still standing, right? So we looked at the effect of what if we use typical connection, even connection that are used in seismic design. So if I have a stud here, how do I typically attach it to the bottom plate and to the top plate? So from the bottom plate, I basically attach it with a nail. Underneath it could be blocking. And typically this is toe-nailed to the blocking. Okay. We have a top plate, typically 2 top plates. And then again you have the floor system, and that is attached with a toe-nail this way to the system. So very, very weak, if you will, right? But you put enough of them in there. We have a provision in Canada that says if you put a nail every 150 millimeters, then you should be able to take forces in plane for seismic load, in plane of that wall, that's sufficient enough. Okay, we said, let's do this and see if it works for a blast design. So we took this block that you see down here, we attached it as you would. We did it at the top and bottom. And then we exposed it to a blast. Nothing, gave me nothing, right? So all we had is a wall at the end of the room. Right? So basically the connection is critical. How could I get those failures before? Well, I put an actual support at the end, right? I put a simply supported steel beam at the end to eliminate the effect of support. But now I want to understand actual support. How does it work? Well, I know it doesn't work. So when we talk about detailing, you see the nails, how they, as the wall is moving out, the nails are just bending. You see at the end of the lab, the sheathing is there, all the studs are there. Nothing broke, right? But huge amount of debris. So essentially, this doesn't work. So we said, okay, what's next? Let's look at different options. We looked at joist hanger, a kind of flimsy joist hanger. These are hangers you use at the end of a joist like this. So assume that you have a concrete wall or something like that. And then you have a floor in the basement that comes in, a floor joist. What you do is you have maybe a top-mounted steel piece that goes like this and like that. And it's just attached to it. So it's just a saddle for your joist. So great. Let me take that saddle and put it at the end of the stud instead. So that way I have a support at the end of the stud. The next option up is a sturdier connection. This one was one of my favorite, and it performs the worst. This was one of my favorite because I figured, you know, it's a strap, it's a hurricane strap. It's one where if you have uplift, you grab the rafter on the roof and you bring it down to the stud. You bypass this, right? So what you do is, let's say you attach it somewhere here, and then it twists, and then you attach it here. Right? It just prevents that uplift from happening. I said, this is great, because when the stud starts bending and want to go out, the strap is going to be in tension, and I'm going to attach it not just to the top plate, which are all the other ones are done that way. I'm going to actually attach it to the blocking. So it's going to work very, very good. So I'll show you a couple of examples of the results. You see here, once you use this hanger, the hanger basically rotates, but it keeps the stud in place. Now the stud is not flying, so I have all my sheathing, I have most of my studs, I have very little debris. So connection actually helped me in this case. It worked well. This is the strap I was telling you about before, my favorite connection. And you see how the end get detached first. All the studs fly out and they break in the middle because we have this system, so you know they don't fly away. But otherwise, the studs would just have flown away. So I was wrong again. And you see it here. You see when we compiled all the material in here, you see all the, well, maybe this is from another test, they just hit the bracket and just laid there. But you see how the failure happened in splitting rather than in tension. Right? Should have known. So because this is a dynamic class, let's do a little bit of analysis on this, because that's exactly what you would do as a researcher or even as a designer of such system. You can't, in a blast situation, you cannot go back and say, well, I look at the capacity, I look at the load, and if the capacity is larger than the load, then I'm fine. Okay? Doesn't work that way, not in dynamics. Because how do you define the load? Is it just the pressure? Is it the impulse? You know, what do I compare with what? So what you need to do is essentially dynamic analysis. What you do, and I'm saying this very, you know, simplistically, what you do is you say, if I have a stud and that stud deflects 2 millimeters, it's within the elastic range. If it deflects 5 millimeters, it's going to start cracking. If it deflects 10 millimeters, it's going to be gone. So what you do in your dynamic analysis is you calculate the deflection, right? You calculate the deflection and you say, oh, it deflected 3 centimeters, so I'm still okay. Or it deflected 17 centimeters, it's gone, right? That's essentially what you do. But in order to do that, you have to include the resistance function, you have to include the mass, you have to include the forcing function, you have to include all of these things into your dynamic analysis. But the output is a displacement. So let's look at a function like this. And this is really where I want you to think a little bit about this idea of single degree of freedom, right? So far in the class, when have you been allowed or comfortable to say, okay, I know it's a complex system, I know it has infinite amount of degrees of freedom, but I'm just going to say it's a single degree of freedom system. Can you give me an example of that?
Typically a water tank.
Say again?
A water tank.
A water tank, right? So you have a column, and you put a very large mass on top, and then you say, it's really the mass of the water tank, and it's the stiffness of whatever is supporting it. So that's a good example of a single degree of freedom, right? There's many things in life that you can't really use single degree of freedom for. For example, what I'm trying to do here is I'm trying to take a beam, and I want to simplify my analysis, right? The beam has a mass, the beam has a stiffness. Surely I can do this. So how do I do this? How can I go from a distributed mass, distributed stiffness, distributed load into a single degree of freedom? Anybody has a clue? Like, do I say, okay, it's the mass of the beam, of the column? So if the total mass is m, so this 10 total mass is equal to m, and I want to go into a single degree of freedom with this, will the single degree of freedom system have mass m as its mass? Ha! Tricky question. Will it have a stiffness k as its stiffness? So I take that beam, I bend it a little bit, I get the stiffness, and I say, I just put k in my system. So I have basically a spring mass system, and I take this mass and I put it here. If the total stiffness is equal to k, I just put k here. Is that okay? How many people think it's okay? How many people don't think it's okay? How many people speak English? It's either okay or not okay. Not okay, thank you. Can you give me a simple reason why it's not okay? What am I doing here? I'm taking a, I haven't used chalkboard for years. I have a tablet at home, so I'm taking a system here where I have mass, 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 and I want to lump it into a mass here. Is that okay? Think about it. But I'll give you something else. I'll give you something that is much more intuitive to understand. I have a distributed load, and this is my mass, this is my single degree, and now I want to turn it into a concentrated load. Now, what I want you to think about is the effect of an arrow right there in the middle on the beam, or on that single degree of freedom, the same as the effect of an arrow at the end of that beam? And the answer, of course, is no. Okay? The question is, how do I convert this from uniform load to a concentrated load? It's not simply taking the UDL and multiplying it by the length. Let me reveal that right away. So what do? We look at our equation of motion as you've known it, and maybe I shouldn't have written it this way. I think Roberto made me aware of this yesterday. So we have the mass times the acceleration as a function of time, of course. Then we have the resisting function as a function of displacement. This is your stiffness, essentially, right? But I'm expressing it in terms of not just stiffness, but a whole resisting function. Okay? It's a force displacement. It could look like this. I don't care. I can just grab it and put it in here, right? So instead of just saying K, because you say K because your system looked like this. Okay? But my system could look like that. So I'm calling it resistant function. And so that's equal to the forcing function. In here, and in here, and in here, I need to put some factors. So I have a mass factor, a resistance factor, and a load factor. Resistance factor and load factor are equal. I don't want to get into the details of that, but think of it this way. I'll explain what these factors are. But as the load is trying to deflect the member, that's the forcing function, the resistance function is nothing other than a function that's trying to restore that same load. Right? So the factor, which is only a function of the shape, is exactly the same. And then I have the Km factor. When I divide Km by KL, I get something that I call KML. And since this is KL as well, I only get one factor on this side. But my apologies for jumping one step because I'm so used to this format, and you may not be. Okay? So, but this is what my function looks like. Let's go through it step by step. First, the KL factor. And I want to explain it because I don't know if you had it in this class or not. No. So you either talk about complete system, multi-degree system, or single degree of freedom system, right? And this is kind of telling you how to go from a complete system into a continuous system into a single degree of freedom system. So you can simply do it by developing these factors. I'm giving you two cases. One case is where you have simply supported, uniformly distributed load, where you get this sinusoidal, if you will, shape. The shape function is up there. And all you have to do is to integrate the shape function in order to get your results. But when you do this for this shape, it doesn't matter the length, it doesn't matter anything, as long as it's a simply supported and it's a sinusoidal function, you actually get a factor. So to go from a simply supported UDL into a point load, point mass, single degree of freedom, all I have to do is multiply by 0.78. If you have yielding in your system, still simply supported, but if you have yielding in your system, for example, in concrete, you'll have yielding first year, and then you'll have yielding at the connections. In timber, you always have pin, and so you only have yielding in one point. If you have yielding, at the point of yielding, this becomes a hinge, right? So if this is a hinge, it's a straight line between them. If that's your shape function, then your factor becomes 0.66.
You just consider the case of ramp mass, so it's
correct.
It's coarse.
Correct.
So, but I mentioned that the general case is not ramp.
Yeah. So how do I go from one to the other? I'm just putting in the equation, you don't have to. But I just want to show you that if I do the math for the Km, I get 0.5. If I do the math for the KL, I get 0.6. If I divide the two, I get the 0.78 that I showed you earlier. But essentially, it's nothing other than taking the integration of the shape function divided by the forcing load. Now the next one is related to this resistance, or sorry, mass. So mass, you can decide to say, okay, the whole column is my mass. If you have a wall, then I take the stud and a representative piece of sheathing on top of that, and I say this is my mass. So mass is typically easy to deal with. You just have to convert it, of course. What about the resistance function? So as I said, my resistance function could look like anything I want. And so you can take that item and test it, get the results, and plug in your resistance function in the equation. What we've done is we've done that. We've tested it. But we've also based it on that T section, and I'll show you the equation in a second. Don't have to remember these things, but essentially, you can either build it as a stud, a sheathing, and a nail, and there's partial composite action between them, or you can take that exact same system and say, I don't care about any of this, I'm just going to test the whole system together and get the response. So this is the response you get from static testing. But this is no static testing, this is no static analysis, so it's dynamic analysis. So how do I convert that into a dynamic resisting curve? Well, I multiply it by a factor that I'll come back to, a factor that basically increases the resistance, might increase the stiffness, and then this becomes my R dynamic, my dynamic resistance curve. And that factor I have to multiply it with is something that we have done also research on. So this is how to convert it from partial composite action T section into an equivalent section. And all you have to do in this case is really, it's all a function of S, which is the nail slip. So all we do is we take the nail, we do a nail slip test, we plug it into this equation, and it gives us what the resistance function is going to be for the whole thing. Forcing function, this is the measured forcing function from the shock tube. So all I have to do is either use it exactly as is, or take a spike and a triangle down and use that as an approximation to my forcing function. And you can see the proximity between what we can calculate and what we have tested in the shock tube, and you can see that it gives fairly reasonable results. The two exceptions on the top right and the one in the middle actually has a story, but I included it in this to show that there is actually variability depending on how you make your assumption. Now that I've laid the groundwork for how we do the testing, how we do the analysis, the next few slides I just want to show you essentially the same thing, but we've done it with glue lam and CLT. So bear with me, it's going to be a little bit fast, but essentially same concept. First we determine what we call dynamic increase factors. So knowing the behavior based on the high strain rate, that could lead to dynamic increase factor. So this is the factor I multiply my static capacity by to get my dynamic capacity. And you see here that if I do static testing, of course I have still quite a bit of variability with an average of this, and I do dynamic testing, I get a higher value on average from the dynamic testing to the static testing, and we do statistical analysis on this to make sure that it's not just a fluke, that there is a significant difference. We've also looked at effect of axial load. You can't see it too well, but look at the effect here. You see there's a fracture here, and towards the end there's kind of a sliver that's just an arch that's keeping everything together, which could break at the end. But that's a behavior of a typical beam. But once you put an axial load on it, you see you get much more compression on that side, and the failure looks a little bit different. So we looked at the effect of both columns and beams. In terms of material predictive model, I don't want to get into the details of this. I don't know if you've done any moment curvature analysis in concrete or structural analysis too, or something like that. But essentially, We have our input as stress-strain relationship. We do moment curvature analysis, and the output comes the resistant curve. And we can match static test and dynamic test fairly well. And we can also match with our analysis that descending, so this is the actual axial load, and this is our theoretical axial load that's shown there. Pretty good in the beginning until we reach a certain point where I think we get a little bit of clamping at the end, so that the axial load increases. You see it in this case, how it kind of jumps up. And so beyond that point, of course, we have too much clamping, and it's not the actual axial load that we're dealing with. The analysis is a little bit different in this case because you take a column, you have a load transfer device, so basically a steel member. You blow the air on the steel member has hinges, and as it moves out, it punches the beam or the column at 2 points. So it's a 4-point bending, right? So 2-point loading. And so what you have is you need a uniform mass, and on top of that, 2 concentrated masses, and you convert everything into a single degree of freedom. So it's a little bit math, a little bit more involved, but essentially the concept is exactly the same. And again, we get fairly decent analysis results from that. We did testing on cross-laminated timber, and I just want to show you an example of that. So these are crisscrossing layers of lumber. We identified 2 failure modes, and again, an increase factor. And this is kind of the fit that we have when we compare our analytical results with the actual experimental results. So I'll try to wrap it up. We did FRP retrofits of beams, and also retrofits of CLT, where, again, I'm really cheap when it comes to these things. You go in the lab and you see that every time they remove a pellet, they take those straps and they throw them away. And I said, why can't we wrap those straps around the transverse layers? They always rotate and they give us this rolling shear effect. So if we just strapped around it, we can actually enhance the capacity. So we did this, and you can see the result of that. Versus the one I showed you earlier.
You could concentrate these
Anywhere you want. Yeah, I have them. I have them at the end. I have them in the middle. I have them longitudinally and transverse. I have them only transverse, only longitudinally. So I mean, it's just like I said, a simple and cheap thing to do. The last part, I know I promised 45 minutes, but I'll go 2 minutes over. The last part is I want to teach you how to design for blast in 2 minutes or less. So the equation is extremely simple. Here, I'll write it down so that you can actually claim after this that you are blast designer expert. If you call S sub S the static resistance, so you know that when you go to the code, it says your capacity is 38 MPa or something like that, right? We know pretty well that there's no such thing as a crisp number on a capacity or load or anything like that, so we know it's a distribution. So if this is our distribution, and this is our S, let's call it average, then we also know that for design, we go into something like 5th percentile, and we take S static, which is S design, right? We know that there's a probability that our capacity is going to be much higher than the S design, but we know there's also a small possibility that the capacity is going to be slightly less than S design, right? We simply cannot control that. So what we do in dynamic analysis, anybody who's done fire design before would know this concept. For fire design, you don't say that the design capacity of this column is this. No, you say the average capacity is that, right? So what we need to do is to go from static to average capacity, and we do this through something called strength increase factor. So SIF is strength increase factor. So that took care of going from design level to average level. And the other one is the dynamic increase factor, which takes into account the, I should have brought you coffee, all of you. So the dynamic increase factor takes into account the strain rate effect. Okay? The fact that the material is not going to behave the same under dynamic condition as they would under static condition. So that's the dynamic increase factor. So here's the trick. You look at the equation of motion. I just told you it's a linear elastic system. Okay, your factor is 0.78 kml, klm. You know your mass. You know your forcing function. Right? You're supposed to. The only thing you're missing is what kind of resistance function do I use? So for that, this is all you have to do. Your S dynamic, or R dynamic if you will, in this case. So S is strength, but it could be resistance, right? Your S dynamic is equal to S static times strength increase factor times dynamic increase factor. You go to the blast code, and the blast code says for light frame, this is for light frame wood, this is 1.9, and this is 1.4. That's it. You get your static capacity times 1.9 times 1.4. You get your dynamic capacity. You plug it in there. You do your dynamic analysis. You get the deflection. You go back to the code and you say, does this deflection means it's broken or not broken? And now you know how to do blast design. I can show you an example of what the code says. The code says, if we're talking about hazardous failure, it means that 3 or more adjacent stud failure with crack extending 50% or more of the stud depth, debris limited to small size. So it tells you that at that displacement, we call it hazardous failure. This is the description of it, and in terms of response, it lies between B2 and B3. I'll come back to this. But essentially what you do is you go to the building owner and say, what do you want? And he says, no more than one stud cracking. I said, okay, I can do the analysis this way, but it will cost you. Right? We charge a lot of money for blast design, by the way. And so what we've done is, to help the designer, to help the code, is we've established that this is a superficial damage, this is a moderate damage, this is a hazardous damage, and this is what we call blowout. We have 4 regions. So we describe it to them, we show them pictures of it, and then finally, the last bit of information that I think you should know about blast design in a dynamic course is something called PI diagrams, pressure impulse diagram. Does anybody know what that is? Okay, so PI diagrams is, let me explain it first, and this will be my last piece. So pressure impulse diagram. Remember when I said earlier that I can have small pressure very close by, giving you a lot of impulse, or I could be far away with high pressure, but what will arrive is small impulse. Of course I can have high pressure and high impulse, or low pressure and low impulse. But what I do when I vary the pressure and impulse, I get some sort of an iso curve. And so this is the funny part, this is the tricky part about this. So we call this impulsive region. We call this, so high pressure. So here you'll have the dynamics, which is where most of the probabilities of an item being falling in there will be. So essentially, I can say in a system that looks like this, that fails at this point, this is the ISO curve that represents that exact point. If I'm less than this ISO curve in terms of pressure impulse, I'm good to go. If I'm larger than that, then the system has failed. It's that simple. Now, and this is the interesting part about ISO curves. If I have a point here, a point here, a point here, or a point here, what's common between these points? They have all received exactly the same damage. Right? So essentially, if I give low impulse, high pressure, high impulse, low pressure, whatever combination, as long as I land on that curve, I have exactly the same damage. Of course, what does that mean? It means that the item has deflected exactly the same amount. Okay? So you see it here, pressure, impulse. Anything that's here, we call that superficial damage. Remember the first picture I showed earlier? The second one is moderate damage, heavy damage, hazardous damage, and blow up. And we normalized all the data we've done throughout the last 5 years, and we plotted them, and this is how we normalize them, but I don't want to get into that. So you can normalize the pressure and you can normalize the impulse in order to fit them all in one. And so you can see the X's and the triangles are all superficial damage observed from our analysis, and they all fit more or less in the superficial region. The squares and the dashes are all moderate to heavy damage. And then the circle is hazardous damage, and then all of these are blow up. So all these are all the walls that literally just blow out of the roof. Okay, so our characterization of the damage and our ISO curves seem to give us fairly reasonable results. Between them, of course, we're dealing with a highly variable material like wood. So whether something sits on one side or the other is in our eyes, at least, is still very acceptable. Okay, and that concludes my presentation.